Alright, hi, my name is Matthew, and today we're going to be talking about the X-ray circuit and its associated components, and the envelope and its associated components, and how they both function. Um, so, before we talk about anything here, we're going to talk about the electricity in the building. The electricity in the building is going to be at 60 hertz at 220 volts, and the electricity will then hit a transformer, run through the building, and it'll come out at 110 volts through the wall. Now, the first thing that we're going to have to talk about is going to be our main switch. So we're going to turn that main switch on, which is important because we got to warm up the machine. It'll trigger the warm up procedure, and the warm up procedure is important because it'll help warm up our the specific parts in the machine that need to be warmed up. So like our filament and our anode. So that's important. We need those to be working at peak performance. And before we talk about all of our points of induction right here, we're going to be talking about our technique. Our technique is going to be 70 kVp at 90 milliampere at 0.1 seconds, and what that will transpire to 9 mass. So 70 kVp at 9 mass is what our technique is going to be for this. So the first thing that we're going to talk about, our first point of induction, should I say, is going to be our auto transformer right here, or our kVp selector. So we're going to input our technique into the machine, into our control panel, and then the kVp selector right here, it'll select the appropriate coil for the setting of 70 kVp. So it's pointing right here. It'll be right by the kilovolt meter. So it's pointing right here. So let's pretend that this is 70 kVp. But let's just say I chose another one like 80. And it can move up or move down depending on what the setting is in the appropriate coil. Now we can jump down here to our second point of induction right here, which is going to be our variable resistor, or our MA selector. And it's going to be kind of like the kVp selector, but this time it's going to be reading our 90 milliampere, our 90 MA. And it's going to use this little hand, and it's going to pick the little setting right there. And it's going to be read by the filament ammeter, which is right here. So now we can follow this line all the way up to our third point of induction over here, which is going to be near our auto transformer. Now that we finished these first 3 points of induction, we can talk about our exposure switch and our timer. Our timer is going to read that 0.1 seconds, and it's going to and the machine is going to read that for the allotted time that we pick. So it's going to be the 0.1 seconds. And the exposure switch, you can kind of describe the exposure switch as kind of like a bridge, in a sense that when you're pushing it down, the bridge is going to come down and traffic can flow through. But when you let go of the switch, the bridge comes up and traffic is going to be a logjam of traffic. So as techs, we have to remember that we have to hold the exposure switch down for the allotted time. So if not, it can ruin the machine and ruin the procedure itself. So like if you let it go before the 0.1 seconds, then it's going to trigger failure or malfunction in the machine, and can possibly ruin the machine's life, or the possible future life that it has. Now that we talked about our low voltage, or our primary circuit here, we can move over to our high voltage or secondary circuit, or what we can call our fourth point of induction with our step-up transformer. So we discussed the 110 volts before. The 110 volts before in the wall, we wrote it down right here, so it's just with everything. And we're going to set that up to 10,000 volts right up here. So we can talk about our MA meter now. It's very important. It's going to double check 2 things for us. It's going to double check our mass if it's right. So our 9 mass, it has to be 9 mass, because that's what our technique is going to be for this one. And it's going to read the power input as well. And 10,000 volts is crucial for the machine to work. If it's less than 10,000 volts, the machine will turn off and it will malfunction and won't work, and it can possibly break the machine in the future. But on the flip side, if it's more than 10,000 volts, let's say it's like 13,000 or maybe even 15,000, then the MA meter is going to catch those and it's going to ground it right here. That symbol right here, that's the grounding symbol, and it's going to ground that and it's going to turn off and the machine won't work as well. So now we can talk about what's going to happen if our 10,000 volts work. So our 10,000 volts, what's going to happen is it's going to be read by the MA meter. It's 10,000 volts. Yay, it works. The machine works. Awesome. That's what we want. What's going to happen is the MA meter is going to put that 10,000 volts into our capacitor right here. I just wrote it down right here just to show it on here. And what that capacitor is going to do is going to trigger the falling load generator. The falling load generator, you can kind of describe the falling load generator as like a dripping faucet. So like a dripping faucet is going to drip down the little water drops constantly. But in this case, the falling load generator is going to drip that 10,000 volts down constantly. Through the machine, so the machine works, and it works perfectly. It works smoothly. So now that we got our 10,000 volts into our capacitor, into our falling load generator, our MA meter's working, our exposure time switch is working, everything's working right now, we can talk about the rectifiers. So the rectifiers is going to change that 10,000 volts of alternating current into pulsating direct current. So it's going to be 10,000 AC to 10,000 pulsating DC. And we have our diodes here. We have our four. It's more than four, but we have four on the thing right here. So they kind of look like the little play buttons right here on like the remotes. These diodes are gonna help have the current flow in certain directions. So that's what we have these little highlighting marks for, is to show what the like which ways the currents are going. So we have two different ways. So we're gonna follow the orange line first up here. It's going to come up here, all the way down here through this diode, all the way through the X-ray tube. Down here, it's going to make a little loop-de-loop here, and finish out over here with the currents. And it's also just like constantly moving as well. It's not going to like stop. So the same thing with the pink line right here. We're going to start down here where we ended with the orange, all the way up here, through the X-ray tube, all the way up through here. And it's just completely constant, and it can go any way. So now that we talked about the rectifiers and the falling load generator, the diodes, the current is flowing, we can discuss our fifth point of induction right here, which is our step-down filament transformer. So we're going to take that 110 volts that we had previously, and we're going to step it down. So we're going to go from the more coils to the less coils over here. So we're going to take that 110 volts, and we're going to step it down to 5 to 15 volts at 3 to 5 amp. And it's going to be alternating current as well. So we discussed our 5 points of induction here on the primary and the secondary circuit with our step-up transformer and our step-down transformer. These are crucial for the machine to be working in a peak performance, in a peak manner, and in an efficient manner as well. So now that we finished talking about this, we can discuss the X-ray tube next. So now we can talk about the envelope. This is going to be our envelope, our X-ray tube. So we have the anode side on this side, and then we have the cathode side right here. So we have our the 10,000 volts of pulsating DC is going to be electrifying our magnets and our stators, and it'll rotate this armature right here. We then have our bearings right here, which will help spin everything, and then we have our tungsten anode right here, which is important because the tungsten metal, it's pretty interesting. The tungsten metal is 3,370 degrees Celsius, so it's pretty hot, right? Now we have our envelope right here. We're going to have our wiring for the filament circuit and the filament right here. And we're going to have the electron beam here. We have the molybdenum neck and base right here. And then we're going to have our nickel focusing cup as well. And that tungsten high heat and nickel will be used hand in hand because it has low negative potential, and it helps that electron beam as well work, which is what we need and what we want, which is very important here. Now on the left side here, we're going to have that 10,000 volts electrify our magnets, and it spins the anode side anywhere between 3,600 to 10,000 RPM, so 3,600 to 10,000 rotations per minute, which works together with the high heat of the tungsten metal. So when with the high heat and the fast rotations working together hand in hand, it's going to help keep that heat down and function, and the machine will function kind of better, right? So now on the cathode side here, we have our filament, and the electrons are released. We have a filament right here, and the electrons are released here. And when the electrons move back and forth, that's what we call thermionic emission. And when they travel in a thermionic cloud, and it hits that target area, and which causes ionization to hit, and makes the X-ray photon, which is what we need. But before we can talk about the X-ray photon being made, we have our low potential negative charge, and that helps us focus it. And we have our grid-based tubes as well, which goes from negative to positive, and it helps saturation current, and all that together is what we need and it's called the actual focal spot, and we need that. So the actual focal spot right here, and so with the actual focal spot, it helps just everything with the target, and then we need the target angle as well with the actual focal spot. Target angle right here is 12 degrees, and it'll help everything flow. It'll help the movement from go one spot to the other, and the target is hitting when it hits the target area, and it bounces out the effective focal spot, and which is what we'll be using on the patient. Like, it's going to be like the light focusing on whatever we're x-raying on that patient. Now that with all that, we have to realize that electrons, they all move back and forth throughout the machine. Some of them won't leave the machine, and when that happens over time, it can possibly trigger a thing called tube arcing, which and that's not good. And that's just like potential failure, possible failure in the future as well. And when the electrons don't leave the tube, that's called the anode heel effect, which is also basically like a little failure. So it goes hand in hand. It's going to end up failing at one point. From there, we have the 12 degree angle right here, and from there we have ionization that happens, and it comes out as the X-ray photon, and that's how pretty much everything is created. So with that, that's pretty much how X-rays are created, with the whole X-ray circuit and then this X-ray tube. So hopefully it all works. Thank you.